Okay, thanks for coming. Today, I'm honored to welcome our own Dr. Yuji Chen, a leading expert in system security with a focus on exploitation research. Okay. So Dr. Chen joined our department after completing his PhD at Penn State in 2022. Okay, his research centered on the exploitation and also the defense. Okay, and his research topic, his current, he will talk about how this, the emerging paradigms such as the quantum computing and also AI can redefine the future of the exploitation and also defense. Please welcome Dr. Yuji.
Thank you. Can you hear me? Yeah, I think so. Okay. So thank you all for being here. The title of my talk is Exploiting Research in Transition from Classical Methods to Quantum and AI Features. So the phrase in transition reflects my research trajectory. On the one hand, the exploiting research has a long history rooted in classical methods, which I believe will continue to work. And on the other hand, I'm seeing new opportunities emerging from the quantum computing and AI, which likely offers the potential for fundamentally different ways to analyze software and to analyze exploits. So in this talk, I will share how my research has engaged with classical methods and how I will explore the role of quantum computing and AI in the next 3 years. Okay, let me start from the most fundamental concept in exploiting research, which is software vulnerability. So a software vulnerability is a flaw or weakness in a program's design, implementation, or configuration that can be exploited to cause unintended behavior, such as unauthorized access or system compromise. Right, so let me give you 2 examples to give you more concrete context. The first example is CV 2021-3156. So CV is a unique ID assigned by the Mutual Cooperation, which is a company funded by the US government. And this vulnerability has a nickname, which is called a Baron Samedid. And this vulnerability is a buffer overflow in the sudo program. You should be very familiar with the sudo program, right? Utility in the Linux system. So by exploiting this vulnerability, attacker can escalate privileges to root on any Linux machine or Unix machine. And the second example is CV 2021-44228. So which is an injection in the log4Java library. And attackers can exploit this vulnerability to execute arbitrary code on any affected servers by logging a crafted string. So according to the US National Vulnerability Database, the number of reported software vulnerabilities has exploded over the past decade. So nowadays, we have more than 25,000 vulnerabilities reported every year. This increasing, so there are 2 ways to explain this increasing. So it's likely because we are having more and more vulnerabilities in the software, or just because we are getting better at finding vulnerabilities, or perhaps bursts. But we don't have a root cause. We don't have the ground truth, right? So we don't know exactly the number of vulnerabilities in software. So we cannot tell. So what's the factors behind this trend? However, the things that we know for sure is we are observing more and more exploits, more and more vulnerabilities exploited in the wild, according to the data from the American Cyber Defense Agency. And this definite increase highlights the necessity and the urgency of understanding exploitation with the ultimate goal of stopping them. So what is exploitation? Exploitation is the process of developing initial small vulnerabilities to something much more powerful that is able to perform malicious operations. Right, so examples of vulnerabilities is what you have just seen, like buffer overflow or some injections. And malicious operation examples, for example, like a privilege escalation that you have just seen, and also like arbitrary code execution. In the past, it was believed that some well-positioned changes to the hardware and the compiler is able to destroy the environment most exploits live. But however, this belief turns out to be a fallacy because exploitation shows surprising resilience and portability. Right, so you can find an exploit which is targeting maybe the Mac OS system, and you can slightly change it, and then this exploit can also run against the FreeBSD system. And on the right, I have highlighted a few landmark exploits across decades. The story started from 1988, where the Morris worm, which is basically the first internet worm, which is exploiting a buffer overflow. And then in 2003, we have another worm. It's also based on buffer overflow, and then become the fastest spreading worm in history. And then in 2014, we have another well-known exploit, which is called Heartbleed, which is a information disclosure in the OpenSSL software. So if you use SSH or use other software, especially in cryptography, you should be very familiar with this OpenSSL. It's the infrastructure software nowadays. And most recently, there's a exploit named Blast Pass, which is a zero-click iOS exploit chance. So you can see, in the past almost half century, we have seen more and more exploits, and we have seen more and more new exploitation techniques, and actually we never indeed stop them. At its core, exploitation research asks two fundamental questions. How does an exploit work, and how can we stop it? To answer the first question, we look deeper into the building blocks of an exploit. So exploit is not created in just one step. It's built out of something which we call them exploitation primitives. Some common primitives, such as include like write arbitrary content to a free heap or free a stack address. And given an exploit, we study what primitives are obtained by this exploit and how attackers obtain these exploits during exploitation. And we also investigate how one primitive transitions to another primitive. And we also investigate how two different primitives combine to form a working exploit. To help you understand, you can think of this process as very similar to the research in biology. The biologists study how nuclear bases combine to form DNA or RNA, which finally encode viruses. And here we study how exploiting primitives combine to form attacks. I want to emphasize that the energy here is definitely not 100% accurate, but just to give you a high-level idea about how exploiting research works. The ultimate goal of exploiting research is not just to understand exploitation, but to stop them. And we have lots of techniques developed to stop exploitation. So for example, we can design new protections, or we can follow the secure by design principles that can prevent attackers from obtaining primitives by exploiting the software, by exploiting the vulnerabilities. But it's very similar to how the immune system or vaccines prevent the harmful DNA from being expressed inside the body. And other techniques, for example, we can use the outcomes of exploiting research to inform vulnerability fixing. Since we cannot fix every vulnerability at once, so we must prioritize the patching of vulnerabilities that are most likely to be exploited. But it's very similar to, as I said, in biology, it's like we can prioritize the treating of the most infectious virus strains. I need to emphasize again, it's like this energy is just to help you understand, and it's not 100% accurate. So in today's talk, I will present two of my works from the past 2 years that exemplify how exploitation research works. The first is called Lancet, which developed techniques to answer the question, how does exploitation work? And the second is called PAT, which developed techniques to stop exploitation, especially attacking the Linux kernel. Both of these works are based on classical methods, which has been practiced and refined for decades. As classical methods continue working, I also see strong potential emerging from quantum computing and AI. So in today's talk, I will also touch on my work on QEX, where we ask how quantum computing could support program analysis and open new opportunities for exploitation research. And I will also cover AI by describing the lessons that I learned from participating in the DARPA's AIxCC competition. In this competition, we investigated how AI can help advance the vulnerability discovery and advance the exploit analysis. Before I start describing these works in detail, I would like to provide an overview of my research that rooted in classical methods. And later, I will provide another overview showing how my research is shaped by quantum computing and AI. Over the past 3 years, we have published, my team has published a series of papers at top academic conferences and industry summits, including the Lancet and the PAT that I'm going to describe today. These works led to strong funding support. We received $64K gift funding from industry and $1.5 million from NSF Safe OSE program, which has been recommended for funding. So please, NSF, give me the money. And our progress has been strengthened by an active network of collaborators. At CU Boulder, I work with Gautam Kaki and his student Kirby on exploit analysis. And we also develop protections together with researchers from IBM and Virginia Tech. None of these achievements could have been made possible without my students. Students basically do the most of the works, and I only give them some high-level results, high-level ideas, and high-level directions. Oops, seems it's not working. Sorry. Okay, so the first work I'm going to present in detail is Lancet. It's a joint work with Gautam and Kirby. Nowadays, lots of memory-safe languages has been used, such as Rust, but the memory error-based exploitation still continues to dominate and remains highly severe. The Microsoft reports that 70% of the CVEs that they address are due to memory safety issues. So similarly, the Google finds that around 70% of the Chrome bugs and over 80% of exploited vulnerabilities are tied to memory safety. And even the Cybersecurity and Infrastructure Security Agency, which is a government agency, they highlight that the memory safety is the #1 in its known exploited vulnerability category. So if you look at the pie chart on the right, and you can see that the memory safety issues alone accounts for the largest share of the known exploited vulnerabilities, which account for 35%. And if we go deeper into the list, and you can see that the out-of-bound write and also user-free, both classical memory safety issues, and consistently ranked among the most exploited weaknesses. So for example, here, out-of-bound write, it has a score over 75, and the user-free has a score over 15. So nowadays, studying the memory error-based exploitation is still the focus of the community. The problem that our work, Lancet, wants to solve is we want to analyze the exploit and to see what primitives does a memory error-based exploit obtain during exploitation. As I said, because primitives are the building blocks of an exploit, so answering this question is really important to understand how exploitation works, and really important for the ultimate goal of preventing exploitation. So one may think that this problem has been solved by existing techniques because primitives are also memory errors. Right? So for example, the primitives like freeing a stack address is also a memory error because you can only free an address on a heap, right? You never free the address on the stack. And also writing controllable data to already free the memory is also a memory error because the memory is already free, so you shouldn't write anything to free the memory. And another primitive, which is called overwriting the global offset table, is also a memory error because only compiler linkers can write to this table. So since the primitives are also memory errors, and we have lots of memory error detectors, so maybe we can apply these memory error detectors to identify primitives during exploitation. But for example, we can use the address sanitizer to detect bugs like buffer overflow and user-free. We'll also use it to detect the primitives. Right, and other error detectors such as memory sanitizer and CETs are also demonstrated effective in practice. So should they also work to identify primitives? So the answer is, unfortunately, is no. So these tools, these error detectors, are good at reporting the initial error, but once the execution of the exploit goes beyond the initial error, they lose clue of the exploitation primitives. This diagram on the right side illustrates this analysis gap. So this is execution trace, and along the execution trace, most of the existing works focus on diagnosing the root cause and identifying the initial error. But once the execution goes beyond this initial error, there's obvious missing analysis gap, which is not covered by existing tools. And this shows a concrete example, which shows what the address sanitizer detects when you are going to replace the exploit of this specific vulnerability. And you can see that the address sanitizer only reports the very first heap overflow and lose clue about what happens following this initial buffer overflow. So if you are willing to spend a week on reverse engineering the exploit and redebugging this exploit, and you can see that after following this initial buffer overflow, there are actually lots of things happened. So at the top, you can see there's a memory move, according to memory move, which is the code that calling the buffer overflow. And it calls memory from one chunk to overflow into another, and corrupting the Tcache chunk here. So Tcache is a caching layer, a caching mechanism in the heap allocator, and it has a very special field which is next, which refers to the next Tcache chunk. So this overflow is able to overwrite the next pointer in this Tcache chunk and have it referred to the GOT table. And following this initial error, the attackers make the program to execute another two actions. The first is going to do another allocation. And because currently the next pointer is already corrupted by the exploit, and it's already referring to the GOT table, so this allocation won't go to the heap region, but go directly to the GOT table, which is in the data region. Okay, and this memory copy is going to copy the value that is controlled by the attacker into the GOT table. So finally, you can observe that the free entry in the GOT table is overwritten by the system. So when the program later is going to call the free API, actually it's going to call the system API. And this system API is going to make the program to remote arbitrary code. Okay, so from the initial buffer overflow to this overlap and hijack, and then finally to this remote code execution, which is RCE here, you can see tons of things that has happened here. And existing tools typically stop at the first step, which is only to detect the initial buffer overflow. And you lose clues about everything following it. And our solution, Lancet, introduced a new technique that can investigate into this exploitation procedure to identify these primitives. The input to Lancet is an execution trace of the exploit to be analyzed. And the output is a set of exploitation primitives that explain how the attack evolves, how the attack evolves from the initial buffer overflow to the final remote code execution. And to achieve the goal, we introduce three core techniques in the Lancet. And the first is a new memory model. So unlike traditional methods, this new memory model explicitly accounts for the memory overlaps and the impact of illegal operations. As such, the Lancet can reason the changes of memory during the exploitation. For more technically, we introduce three ownerships in this memory model. So one is the CL owner, another is the value owner, and the third is called the pointy owner, to keep precise track of how the memory is controlled and manipulated by the attacker. So the right side shows you a concrete example of how the ownership works when you are going to do an allocation. So when you do an allocation, you will have one pointer referring to the newly allocated object, right? And let's say we have two subjects here. Subject A stands for the newly allocated object, and subject B stands for the pointer. So after this allocation, the cell owner of all the cells belong to the object becomes the subject A, indicating that currently the subject A is using these memory cells. But still, the value owner of these cells are still the allocator because we haven't written anything into these cells. Okay, and we have a pointy owner of the pointer. So this pointy owner of the pointer is referring to subject A, indicating that this object should always refer to this object. Okay, and we update this memory model through some operational semantics on intermediate representation, which is called Lancet ISA. And you can see the operational semantics example here. So right now, if with this newly allocated object, if we are going to read something from this newly allocated object, it is uninitialized read, which is a primitive. And we detect it is because the cell owner of these cells and the value owner of these cells are not consistent. And also, if right now we are going to use the using pointer to write to these memory cells, also another primitive, is because the pointy owner of the pointer is also inconsistent with the value owner of the cells. Right, so we base on these principles, and then we define a set of primitives, form a definition of the primitives. And this is an example showing like how we define the primitives. Okay, so with these operation semantics and with these definitions, we are going to analyze the execution trace of the exploit, and finally we can get results like this. So with our solution, we can systematically identify exploiting primitives, and this screenshot shows part of the output of our tool. And you can see there's something highlighted here. It's basically an exploit primitive, which is exactly the overlap primitives highlighted here. And this demonstrates how our tools can identify the critical building blocks of the exploits that and how these primitives drive the exploit forward. Yes.
So your Lancet tool will basically getting the input as a executable, or is that something that intermediate representation like object?
So the input to this tool is actually the execution trace of the exploit. It's a sequence of instructions. It could be x86 instructions or ARM instructions or like RISC-V instructions.
Is that the bytecode level or
binary level? Right. So actually, this tool doesn't rely on the source code. It can reason over the at the binary level. Yes.
What properties of primitives they need to have for you to be able to develop it? Do they need like memory access these? Do you capture like microarchitectural side channels or?
Yeah, unfortunately, it cannot capture the microarchitectural side channel because our definition of the primitives are based on the memory corruptions. Right. At least, I mean, for this, for the current version, it's yes.
So these primitives identified in conjunction with like the identification of the memory errors, or is this separate? Is this separated completely from the memory error side of it?
Yeah. So the current the primitive definitions focus on the memory errors, so it can identify the primitives caused by the memory errors and also the memory error itself. Right. Yes. Exactly. Yes. Oh, sure. For the guy in the room. Okay. Any other questions? Okay. So Lancet is the first system that can automatically identify exploiting primitives from an exploit trace. And unlike existing techniques, which usually focus on the execution before the initial error, focus on diagonizing the root cause and identify initial errors. So Lancet goes further, and it is able to reason the execution following the initial error. And looking forward, I plan to extend Lancet in the next 3 years. So first, my team is going to port Lancet to the QEMU environment so that we can analyze the exploitation targeting the operating system kernel and the exploitation targeting the firmware. And second, the current Lancet can only identify primitives. it cannot reason about how one primitive transition to another primitive, and it cannot reason how multiple primitives combine to form the tag. So the next step is going to triage the transitions and the combination of the primitives. And finally, my plan for the next 3 years is the modern attacks often span multiple cores and devices and privilege boundaries. So for example, the figure on the right shows 4 examples of exploit chains. Right, so the chain 1 starts from the browser exploit and into the application CPU, and the chain 2 starts from the baseband microcontrollers and jump to the application CPU. Chain 3 and chain 4 start from the Wi-Fi chipset and finally go to the application CPUs. Right, so the modern attacks is actually exploit chains and will generate multiple traces when you are going to replay it. Right, so my plan for the next 3 years is also I'm going to analyze the multiple traces generated by the exploit chain and to see how these exploits are chained together. Okay, so that's my first work I want to describe. And the Lancet exemplifies one example of the exploiting research, which is trying to understand exploitation. But understanding exploitation is not the ultimate goal. The ultimate goal is trying to prevent exploitation. And the second project I will present very soon, the PAT, takes on this challenge. It's a joint work with my students as well as collaborators from IBM and Virginia Tech. So it currently takes nearly 2 months for a patch to be developed and merged into the upstream Linux kernel. The delay is due to several factors. For example, the Linux community is shortage of manpower, and patching needs special expertise, and also the Linux community has a strict commit merging policy. So a number of these challenges can be easily resolved. So the situation that it takes 2 months to do the patching will persistent in the future. And for vulnerabilities that has been publicly disclosed and don't have a patch yet, we have a special name for them, which is called a one-day vulnerability. And it turns out that all Linux vulnerabilities are one-day vulnerabilities because you can easily find them from the mailing list of the Linux kernel. The right side shows an example. The screenshot shows the example is like you can easily identify a vulnerability that has been reported, but we don't have a patch yet. So while the patching vulnerability is takes a very long time, develop an exploit is much faster. So typically, capture the flag players can often sprint an exploit over a weekend. And it leaves a time window here is like after the vulnerability is disclosed and before the patch becomes available, there's almost a 2-month time window where attackers can write the exploit and launch attacks. And our patch work is trying to mitigate this problem, trying to harden the Linux kernel against the one-day vulnerabilities before their patches become available. Existing kernel protections are limited in alleviating this situation. So in general, existing Linux kernel protections fall in 2 categories. One is randomization-based defense, such as ASLR. ASL stands for address-based layout randomization, which is randomized-based attack, and structural layout randomization and heap cookies. So all these protections depends on the fact that attackers don't know a secret number. But these attacks can be defeated by something we call information leak. It's like when the attacker have these secret numbers, they can easily bypass these protections. Another category of the kernel protection is the isolation-based protections, such as SMEP, SMAP, and the CR4. Unfortunately, these protections are often bypassed by attackers using the control flow hijacking primitives. For example, you can see the code on the right. So if the attacker is able to hijack the control flow to execute this function, and if the attackers have control over its argument, so attackers can write a malicious value into the CR4 register. And the CR4 register is a control register. So attackers can easily use this code snippet to disable the SMEP and SMAP. So my observation here is the Linux kernel protections are often bypassed because they often because they operate at a later stage of the exploitation where attackers already have a very strong primitives to bypass these protections. Right? For example, attackers already have control flow hijacking so that they can bypass it. Attackers already have information leak so that they can bypass it. And this meme basically shows this situation, yes, the protection, the primitives already outpower the protections at the late stage of the exploitation. The key idea of our solution, our PAT solution, is to shift the protection from the late stage of exploitation to the very early stage of the exploitation, and we are going to directly preventing vulnerabilities from being triggered. The idea is if the vulnerability never gets triggered, attackers, of course, cannot do any exploitation. Right, so how do we prevent the vulnerability from being triggered? So input to the PAT is the one-day vulnerability report, which tells about some technical details about how this vulnerability is triggered. And the output of the PAT is an eBPF program. To give you some background, the eBPF program is conceptually very similar to the loadable kernel modules, if you have ever taken the operating system course. But they are safer and more flexible because they can be installed into the kernel without stopping the kernel, without recompiling the kernel image. So we taken the one-day vulnerability report as input. The PAT will generate an eBPF program and then install the eBPF program into the kernel. And this diagram shows what exactly the eBPF program does inside the kernel. So this eBPF program is going to check if the triggering condition is met before the error site. And if the triggering condition is met, and then the eBPF program is going to skip this error site and jump directly to this return instruction and have a Linux kernel directly return back to the user space and carrying the malicious process. Yes?
There can be false positives because the trigger condition could be over approximation of actual.
Yeah, so you're asking like whether this design will have false positives. Right, so it depends on how we design the policy. Right, if we design policy to be very conservative, and then we won't have false positive, but we'll have false negative. If we design the condition to be very aggressive, and likely we'll have false positives. So in our current implementation, the condition is designed to be very conservative because we don't want to kill any benign processes. Okay, other questions before I continue? Okay.
So
yeah.
That you need some kind of manual intervention from the eBPF program.
It's automated. Okay, so let me explain why how it is automated. Okay, so let me first walk through a concrete example here. So in this example, it's a buffer overflow. Okay, and in this example, the error site is at line 645, where there's a buffer access, right? And the index to access this buffer is a size, which is obviously incorrect because if you still remember, in the C language, index starts from 0. And this is a very typical off-by-one buffer overflow. And the triggering condition of this buffer overflow is when the size is equal to or larger than the page size. Because in this special case, the size of the args buffer is the page size. Okay. And the PAT is going to prevent this vulnerability, prevent this buffer overflow to being triggered. The PAT is going to install a BPF program that's going to check whether this triggering condition is met, and if it's met, and then the eBPF program is going to jump to the line 693 and return with an error code to indicating that there's something awry in this piece of function. Okay, so let me talk about some technical details, how I automate this process. The first step of doing these things is, of course, to locate the error site. Right? Without knowing error site, we don't know where to stop exploitation. But to locate the error site in the vulnerability report is very easy because if you see the vulnerability report here, it directly tells you which instruction caused this buffer overflow. Okay, but it's not enough because this vulnerability report, all the information reported here is corresponding to an image which is called a sanitized image. So sanitized image is different from the native image that's running in production. So sanitized image have some instructions instrumented. So the first step in our automation is going to translate the error site in the sanitized image to the native image. And what we do is going to first find the error site in the sanitized image and then map it to the source code level. And then from the source code level, we map it again back to the error site in the native image so that we can precisely locate the error site in the native image. And the second step to automate it is, of course, we're going to construct the triggering condition. And to achieve this, we have a condition schema for each vulnerability class, including integer overflow, user-free, out-of-bound access, and also data race. And from the condition schema, we are going to derive some templates that can encode the triggering conditions at the error site. So right side shows an example. Yes, we have an out-of-bound schema, and in this schema, it's going to say the access address is expressed by the BPF get start and also BPF get length. And BPF get start and BPF get length is the two helpful functions that we introduced to get the base address of the object and the size of the object. And the access address must fall in this range. And this diagram shows the architecture of our design. Is like we have lots of condition schemas for different vulnerability types. And these schemas are vulnerability dependent and they can be extended. But underlying these schemas, we have lots of infrastructure mechanisms that can be commonly used. Okay, and all these infrastructure mechanisms I have already described the report processor and also the mapper. And the last piece of this infrastructure mechanism is called checkpoints and the restore. So checkpoint and restore are important here because we want to avoid kernel panic, because we don't want the kernel to panic after we directly return from the error site. So the checkpoint is we are going to first store the register context at the entry point of the vulnerable function. And once we detect the error, we are going to jump directly to the return instruction, and we are going to restore the register context back to the context when the kernel just entered this function. The only change that we made here is we are going to reset the AIX register to this error code to indicate the error. Okay, so in this case, when we return from this function, the context of the kernel is still preserved. And of course, we have some special handling for these special cases, right? So because in the kernel, there are lots of paired operations, for example, lock, unlock, memory allocation, and memory free. So we will also take care of these paired operations to ensure that the lock is unlocked and the memory is freed to ensure a great restore and avoid introducing inconsistency. Okay. So this design is effective, but I know most system engineers care mostly about the performance overhead, and the results shows that the performance overhead of the pad is negligible. Okay. So my own biggest takeaway of this pad work is not how useful it is, but it's actually how expressive and efficient and safe the eBPF is. So the pad design is possible only because the eBPF's expressiveness, efficiency, and the safety. Okay, and I have long envisioned that eBPF will play a critical role in system engineering, and my prediction is turned out to be true because in recent years, the eBPF has recently been widely used for synchronization in the kernel and for storage, for performance, and for performance optimization. So looking ahead, one exciting direction for the next 3 years is what I call eBPF machine learning enabled intelligence operating system resource management. So I'm going to use machine learning to do the resource management in the operating system kernel, and I'm going to embed the machine learning models into the eBPF for its flexibility. So the motivation of using machine learning is because there's no one-size-fits-all policy that can work for all applications. So typically, what works well for one application may perform poorly for another, and the machine learning can help by learning to optimize all the resource management, including CPU and memory. And the reason why I believe eBPF is a good way to install the machine learning models into the kernel is because implementing new policies directly in the kernel is always very hard because you always need to recompile the kernel you always need to reboot the machine, and you always need to have a long debating with the Linux kernel communities to have it emerged. But with eBPF, you can easily install your new policy and have it into the kernel. And this diagram shows how exactly it works at a very high level. Is you can collect lots of performance events from the underlying hardware and then train it in the user space and get the model and have the model installed into the eBPF maps. And then you can run the inference logic inside the kernel and using the results of the inference to control the hardware. So I believe this design will become a platform for rethinking how the operating system itself can be made adaptive and intelligent. Okay. So both Lancet and the path that I just described are based on classical methods. While these classical methods continue to work, and I've also seen new potentials from the quantum computing and also AI techniques. So this exploration began when I joined the CU Boulder, and it has produced several outcomes. We have published 3 papers at venues such as QCE, Black Hat, and SpaceSec, and I'm going to present the one published in QCE this year. And in addition, so in the past 2 years, I put lots of efforts on the DARPA AIxCC competition, and the cyber reasoning system that we built ranked the #1 in the self-assessment and #2 in the vulnerability discovery out of the 7 teams in the final. And I will also cover the lessons that I learned from this competition in the following slides. And these results were made possible thanks to the Research and Innovation Office seed grant, and also the $3 million from DARPA to the entire team. I'm also very grateful to my collaborators, especially Rami, for his support in quantum research, and also colleagues from both the US and Canada institutions. I cannot list all their names because we have our team is very huge. We have more than like 20 members in the team. Also, none of these achievements would have been possible without my students. They have done most of the work, and most of the time I just gave them some high-level directions and high-level ideas. Okay, QEX is my ongoing efforts to explore how quantum computing can be applied to security problems, and it's a joint work with Rami. So one of the key challenges that I encounter in my exploitation research is I find it's very hard to explore as many exploitation-related programs as possible. The reason because of the state explosion problem. So state explosion problem states that the number of possible program states grows exponentially with program size, and it makes exhaustive analysis infeasible. And the classical techniques try to address it, but they oftentimes run into limitations. So on the right, on the right side, you can see that the middle region is the ground truth, is the exploitable states. So some classical techniques will over-approximate this state. For example, the abstract interpretation, they will include lots of false positives in their results. And some techniques tends to underestimate these exploitable states, and they will miss lots of exploitable states in their final results. So as a consequence, the results from classical methods either underestimate or over-approximate lots of the exploitation research. For example, they will underestimate the true severity of vulnerabilities, and oftentimes they will overestimate the actual effectiveness of protections because they cannot have a sound and complete collection of the exploitable states. And I believe that the quantum computing can be helpful here because of the quantum computing has 2 unique features. So the first feature is superposition. Unlike a classical bit that either 0 or 1, so a qubit can exist in a superposition of both 0 and 1. And this notation indicates how it could be. So the alpha and the beta here are called amplification, which indicates the probability of the qubit being 0 and 1. Okay, so in this case, with n qubits, we can encode in total 2 to the power of n states of the program. So it means that the number of qubits to represent the program states only increase linearly with the program size. But the classical methods, the resource needed in classical methods increase exponentially. So in this case, we can avoid state explosion using the superposition, and there's no need for over-approximation and under-approximation using quantum computing. And a second feature that why I think quantum computing could be helpful is its feature is entanglement. So when two or more qubits are entangled, their states are interdependent, right? And changing one immediately change another. So this property naturally captures the dependencies of the dependency between program variables that are critical in reasoning about the exploits. On the right side, it shows a situation like this. So you can see we have two qubits here, where one is x and another is y. So they are either both 0 or both 1 after you assign the value of y to the x. So this naturally captures the data dependencies between different variables in the program. To leverage the two unique features, in the QEX, we propose a design that produces a quantum circuit that is equivalent to the target program to explore the program's state space. And here is an example, super simple, right, with branch prediction and the true branch and the false branch. And on the right side, you can see the equivalent quantum circuit. So we have 3 blocks here, the green block, blue block, and also a pink block. The green block represents the branch prediction. And the results of this branch prediction is in superposition, which enables the parallel execution of both the blue block and also the pink block. And the blue block is going to execute the truth branch, and the pink block is going to execute the false branch in parallel. And finally, the results of both branches is going to be in a superposition state. So in this case, the that variable can be represented as this. Is like it's saying if the x is smaller than 5, that is equal to y plus 1, and if x is larger than 5 or equal to 5, and that is equal to x plus 1. And this is a superposition to represent the value of z. And the execution of both branches can be completed in parallel. And of course, this representing also saying that that is entangled with x and y. So the data dependencies between variables can be naturally represented. Okay. And this page shows our experimental results that are based on simulators. So for the baselines, we compare with Grama-3, which implements the abstract interpretation, and we also compare it with Angle, which implements the symbolic execution. So these tools are basically the tools that I frequently used in my exploitation research. And the metrics used here are over approximation rate and under approximation rate. In the table, you can see there are lots of numbers larger than 100%, which indicates over approximation. And the timeout is treated as under approximation because the tool cannot collect all program states within the given time limit, so it only collects partial of the program states. So from the table, you can see that both classical tools have either over approximation or under approximation, but our tools has no over approximation and approximation. Yes.
How do you able to execute QEX? What was the execution time for QEX?
Execution time for QEX from like 3 hours to 4 hours.
Actually, quantum machine or machines?
No, for this, we are based on a simulator. Right. Okay. Any question? Okay, let me continue. So actually, Gautam has already asked this question. Yes. So while these results show promising, but the system, the quantum computing right now is still constrained by the current hardware, and the much work demand to be realized to realize the QEX envision. And the limitation that I care most is actually the resource consumption. So what we observed in experiment is for a program with near 3,000 lines of program, it requires 1,000 logical qubits and 1 billion quantum gates to finish the analysis. But the good news is that quantum hardware is advancing rapidly, and this figure shows like the steady increase in the number of physical qubits in recent years. So today, companies like Atom Computing, which is a startup in Boulder area, already have quantum processors with 100 qubits. And Looking Group from Harvard published a new Nature paper this Tuesday saying that they are currently able to manipulate 3,000 qubits in their machine. Right. So I'm very positive about this. Like I'm foreseeing like maybe in 1 decade we will have a quantum computer powerful enough to do this experiment on a real quantum computer. But the problem here is having enough qubits is not enough. It's not enough on its own, and we need to have some computer system that are capable of controlling qubits at scale. So in the next 3 years, I will focus on developing a quantum control system that can scale to support 10,000 superconducting qubits, and I will achieve this through collaboration with the Lawrence Berkeley National Lab. And our plan is we are going to release version 3.0 and 4.0 by the end of this year and the next year. And in the meanwhile, I will also going to explore at the algorithm level to see if we can find new algorithms that can reduce resource consumption for quantum computing-based program analysis. Okay. Beyond the quantum computing, another elephant that I cannot ignore is AI techniques, especially the large language models. Right? And I explore this direction through the DARPA and the AIxCC competition, which is also with foundation model support from Google, OpenAI, and Anthropic, and Microsoft. So this competition is a 2-year competition, starting from 2 years ago, and the semifinal is last year, and finally 7 teams enter the final, and our team is one of them. And during the competition, we design, test, and improve the AI-powered cyber reasoning systems. And the goal of the cyber reasoning system is to automatically find vulnerabilities and patch vulnerabilities. The competition focuses on C and Java, and it has 2 modes. And the vulnerabilities in the competition is either introduced by the DARPA staff, or they are 0 days in the software that they used. And also, there are 2 modes. One is the full scan is going to find the vulnerabilities from the entire software, and the delta scan is going to only find the vulnerabilities from the code commit. And the scoring in AIxCC is based on 4 key capabilities of the system that we built. The first is the vulnerability discovery score, which measures how well our system can find vulnerabilities. And the second is program repair score, which values like whether the patches that we submit can remove the vulnerability and also preserve the software's intended functionality. So some naive way to remove vulnerability, for example, just to comment the vulnerable code won't work. And the third is the serif assessment score, which is going to evaluate the serif reports sent by the DARPA to decide whether a received report is correct or incorrect. And the final is called the bundle score, is like whether your system is able to correspond a patch that you generate with the vulnerability that you discover. Okay, so how did our team perform in the final? On the achievement side, we ranked first in the serif assessment and second in vulnerability discovery. We submitted proofs of vulnerabilities spanning 10 different CWEs. Our system successfully analyzed the software based over software with 5 million lines of code. Or other teams cannot achieve this at this scale. And we discovered the most real-world vulnerabilities. So to sum up, our system is really good at finding vulnerabilities. But then on the repair side, things didn't go as well. We only managed to submit 4 patches during the entire competition, and only 3 of them are correct. And as a result, we finished number 6 in program repair, which dragged us down to 6 overall. So what happened? It turns out that we have a third-party dependency in our system, and this dependency is called beer, and it stored our patch generation for entire 4 days, so that we didn't generate any patch, and we didn't actually submit any patch during the 4 days. And we didn't have a watchdog mechanism to recover this failure in our system. So I spent almost all my past 2 years on this competition, and the final results was not what I hoped for. I think it's totally fine to make mistakes, but I don't think it's acceptable to not learn lessons from it. So you might think that the lessons that I learned is like I should always add a watchdog to the system, and I should always do stress testing in the system. But I mean, these, of course, they work in the short term, but I don't think they really address the deeper issues. So I think the real issue here is our system wasn't AI enough. And I aggressively believe that all the heuristics, all the rules in the system should be replaced by the AI. And my belief is based on the following observations. Right, so the first observation is actually a rule-based system is not reliable. Right, even if we added a watchdog, it's very likely that we will stumble with missing other rules. Right, and second observation is the foundation model is evolving much faster than we initially expected, and we don't foresee it. So we don't use lots of heuristics in our system. And the last observation is, I know there's no evidence that a foundation model reason, but the foundation model is really good at integrating tools. And currently in our system, all these things are done by rules. So in the next 3 years, my goal is going to develop a fully agentic system for exploitation research. And I'm going to replace all rules in our system with agents wherever possible. And in the meanwhile, I'm also going to collect some data from the system so that I can use the data to fine-tune the underlying foundation model that we are using. And this diagram basically shows a high-level idea. It's like we have agent to orchestrate different tools. These tools are designed for exploiting research, and we are going to form a feedback loop here, collect data, fine-tune the model, and use the model to orchestrate tools. And I will achieve it through the collaboration with researchers from some other universities. Okay, I think that's all for today's talk, and I don't think I have enough time to finish the summary and the roadmap, which is basically repeat what I have said. Yeah, basically repeat what I have said, what I have done so far, and also the future roadmap. Okay, so I think I should stop here, and I'd like to open the floor for questions.
Let's take a quick questions.
Oh.
So I have some personal question. So you said 3 years, right?
Mm-hmm.
So any reason that you put 3 years there?
So the 3 years have nothing to do about the technical part. It's all about like my roadmap to get tenure, because I'm supposed to submit my tenure package in 3 years. Right, but actually we already have some preliminary results here. So for example, this agentic system, because we already have all the tools, right? We just need to going to develop an agent to replace the heuristic in these systems. So actually, we have planned to submit preliminary results of this system to ICML next year. So I think at least for this project, I'm able to finish within 3 years. Yes.
Aspects of this that you're like hesitant about replacing with agents, right? Like, are there places in which you think that maybe the rules actually are sufficient? You're going to kind of keep those there.
Yeah, right. So yeah, your question is like, because I said I'm going to replace all the heuristics, and your question is like, do you know any part of the system that cannot be replaced by the AI, or at least the AI is not that efficient, right? So if you think of this question, is like if you are going to design an AI-enabled system to find the vulnerabilities, so the idea that jumped into your mind may be like, okay, I'm going to use foundation model to retrieve the code and scan the code and have the foundation model to reason by itself to see if it's able to identify code according to some patterns. So actually, when we design this system, this is our first solution, but it turns out it's not very effective. Right, so my answer to your question is like, if it requires foundation model to reason, please don't do that. Okay, and my estimation of the intelligence of current foundation model is more like undergraduate students at its 3rd year or maybe 4th year. Okay. Do I answer your question? Okay. Okay. Other questions? Yes.
Like agentic AI tools, I find that they're fairly effective, but I find that I have to supervise it pretty closely in order for it to like work at a high success rate. So how can you like ensure this system is able to work correctly at a high rate of success without like any sort of like supervision?
Yeah, so you are asking like, how can I make sure that the system is working well, because based on your current experiences, they must have a human handler behind the foundation model, right? And I would say like there's no way to guarantee this. So even the biggest, I know the results is like they have a benchmark which is called CWS, and even the best foundation model that we have nowadays can only have a 59% success rate to analyze this code. So my answer to this question is like we don't have a way to guarantee that. But we have a 59% possibility to have a good results. That I think that's already enough. Okay. Other questions from the audience? Yes.
What would the full benefit from in general?
So you're asking like what would be the benefit of quantum computing in the security? Yeah. So what I have explored so far is like you can use quantum computing to explore the program states soundly and completely. If we do have a very useful quantum computer. Okay.
Okay, I think it's a time up, and thanks to the speaker again.